Hi, in this video, we want to take a look at transforming our variables to improve our multiple regression model. All right, so what we want to do, we want to come up with some way to algebraically change our variables so that we get the best regression model possible. Now, first thing you need to remember when I'm doing something like this, I need to make sure that my transforms are something that my audience will accept. So if I build the greatest statistical model ever, the greatest machine learning model ever, and the end users, the decision makers don't accept it because they don't trust it, don't understand it, it's worthless. So it's better to go simple mathematically with something that gets used than to do something that is really actually a better model that gets thrown in the bin. So keep that in mind as we go through this. Okay, so we're in the situation that we have multiple predictors and we have one target variable, and we want to be able to model that one target variable very well. All right, so what I'm going to do, let's say I'm building my model, and then I take a look, and I'm really not satisfied with my model. All right, well, one of the things I can do, I go through and I look at my scatter plots. Remember, scatter plots are our most important diagnostic when we do regression modeling. And I see, hey, like I've got skewed data, or I don't like the distribution of my predictor variables, or things really aren't working out on that target variable. What can I do? All right, so what we're going to do, we're going to use R to find a way to transform the variables into a more useful format for the data. Now, how we do this matters, because what I can do, I could just jump straight to my target variable. I could hit just my predictor variables. I could do target variables and predictor variables at the same time. I could hit the target variable without considering the predictors. I could hit the target variable while considering the untransformed predictors, or, and this is the one that I think you should use in multiple linear regression, I could transform the target variable while considering the transformed versions of the predictor variables that I've already transformed. That's the way that I feel like you should do this. Now, I'm going to call this sequential transforming. You transform the predictor variables, then you transform the target variable. I feel like that's the best way to go in multiple linear regression. In simple linear regression, the sequence honestly isn't as important in my experience. And now that might just be from the data sets I've happened to handle. But if you transform Y with or without considering the predictor variable, I don't really see a big difference in simple linear regression. But when we get into multiple, you want to do it sequentially. That's my personal experience. And my opinion is that you always want to consider your predictor variables if you're transforming a target variable for a regression model. All right, so this example is modified from the textbook's website. Here's the website. The textbook is free to download from UCF's library if you're a student. Okay, so here's what we can do. First and foremost, we could not transform any variables. And that's one we always need to consider doing. And why would this be the way to go? Well, if my audience doesn't really trust regression in the first place, if I start throwing in some college algebra, functions into the mix, they're going to trust it even less. So sometimes the simplest model that they will accept, even though you can do better, is the way to go. Now, next thing we want to consider is transforming only predictor variables. Now, next one we can do is we could transform the target variable as a univariate variable that it has no dependencies on predictors. I do not recommend this. This has less shortcomings in simple linear regression, but the more variables we have in predictors, the less I like this. Next one we can do is I have the option of transforming my target variable based off of untransformed predictors. And this would be the way that I would want to go if I wasn't going to transform my predictor variables for some reason. And here, I can transform my predictor variables, then transform my Y variables. So if you're going to transform your target variables and your X variables, my opinion is that you should do X and then use the new transform predictors to transform your Y, your target variable. All right, so let's go ahead and get into the example. We're going to be using the magazine's data set from the publisher's website. And here I'm just loading the data. Now, here we have a categorical column, categorical variable, which is the magazine name. And that's an identifier. So I go ahead and change all my row names to the magazine name. That way, as I'm looking through, it's easier for me to spot things when I do my diagnostic plots. And I always like to sort my data by an important variable. That way, it's easier for me to spot possible trends as I look through stuff, as I'm looking through the data. So I go ahead and reorder it by the target variable. Now, if you've been watching my videos, you know I always color the points by an important variable. And so I'm just gonna go through, I'm gonna color all of the points by the target variable. And all of this is just, okay, here are all like the possible values that I could get if I go from the minimum to the maximum. They're all integer values. So I do a step of 1 on the by statement. Now here, I'm getting the colors. So here, this is all the values that I could get from the minimum of my observed target to the maximum of my observed target. And then I go ahead and I tack on the colors onto my data set. I'm not redefining this over and over and over, and I'm storing it on my data set. That way I can easily pull it up down the road. Okay, so what we can do, so first thing I'm going to do as I'm building models, I'm going to start with the vanilla model. I'm just going to take the target variable, and I'm going to throw in my predictors, and boom, I get something. All right, so let's take a look at what we get. All right, so right off the bat, I see that the slope is non-zero, like pretty strongly on all three of these, all three predictor variables. I see that I've got 0.72 R squared, and my F-test is within machine accuracy of 0. All right, so it looks like I definitely have something in there. There's something worthwhile. All right, so now I go ahead and I run ANOVA. Remember, ANOVA is checking to see if I have the intercept model, should I add pages to that model? If I have the add pages simple linear regression model, should I add sub-revenue? If I have add pages sub-revenue predicting the target, should I add news revenue? And if I have these three predictors, should I, oh, well, there's no more. All right, so, and I can see, you know, the p-values. And just let you know, before I made this video, I sorted my predictor variables in the ones that look like to me most important to the least important. That way I have a good feeling for what's going on. Okay, so now let's go ahead and do a pairs plot. So you'll see what I've done is I'm just taking the 4 variables, the target and the 3 predictors. I go ahead and I plot things, and, you know, just to get a feel for what's going on. Remember, the scatter plot is our most important plot in regression. So up here, my vertical axis is my target variable, and then along here, here, and here, I have my predictor variables. Now, when I look at this, I can see that, you know, it's like my target variable is like all bunched up down at the bottom on all 3 of these. Also, it's like everything is kind of clumped up. Everything's kind of clumped up horizontally, and everything's kind of clumped up horizontally also. All right, so maybe I've got some skewness, something like that. So I'm looking at that, I'm like, I might be able to do better. And if I can do better, I want to do better. And here, I can't really, everything's so bunched up, I really can't interpret if there's any relationship between my predictor variables. All right, so what I can do, I can transform the predictor variable. So like each one. So here, this is actually the target. Messed up. No, I was right. I didn't do that. All right, there we go. Okay, so what I'm going to do, I want to predict the add pages predictor variable. Now, that is an independent variable. Since it's independent, something that's important, you'll notice I put tilde1. This is saying that there are no variables that add pages depends on. This is an independent variable, therefore it does not depend on anything in my modeling structure. And so what happens when I use power transform in the car package, I can see that, if I run the summary statement, I get an estimated power transform. Here's the rounded power of the transform. And here I get a walled confidence interval. And you'll notice that 0 is inside that confidence interval. Now, what I recommend that you do in real life, all right, so let's say I'm building a model and nobody is going to look at this. Nobody's going to see it. Nobody's going to question it. In that scenario, I would go ahead and use this value for my power transform. Now, let's say people are going to be looking at this. People are going to be digging in, and people are going to be, I need to justify what I do. Well, does 0.0934 sound like a comfortable number? No. It's not a number that people will readily take to. It's not a number that people will feel comfortable with. And so they're going to sit and they're going to pause and they're going to think about that number when you explain it. If they're thinking about that number, it can only hurt them accepting or rejecting your model. So I want to give numbers that people are comfortable with. I want to give them things that feels more familiar. That way they're more likely to accept it. So what I do, I look at my confidence interval and I look to see, is there a number in there that would be more comfortable to average people? Well, I can see that I've got like 0 in there. I've got 0.25 and like -0.1 is in there. And 0.2 are all like viable options. Well, 0 is, is the rounded version of this. And that's probably going to be the most comfortable one. Now remember that when I have 0 for a power transform, that's actually the log transform because of limits from calculus. Okay, so what I will choose to do, the transform for add pages will be the log transform because that's the one that I think my audience would be most willing to accept. Let's say I've dealt with people before in my decision makers, and I know that they don't like logarithms. Then maybe I would take like 0.1, 0.2, 0.25. I would lean towards probably 0.2 in this. Maybe 0.25 is like 1/4. So if I'm doing like a 4th root will be more readily accepted than a 5th root, more accepted than a 10th root. So I want to keep it like relatively simple roots. All right, let's go to the next one. Let's look at sub-revenue. So sub-revenue, we get a -0.0626. Once again, that's a number that my audience isn't going to readily accept. If no one's going to look at what I'm doing, I'm just going to go ahead and use that power transform. But if people are not going to be looking at it, or sorry, if people are going to be looking at it and I have to explain it, I want something that's more readily accepted. So I'll go ahead and look at this. And I think 0 is a good choice. Now, also, the summary statement goes ahead and it gives us a hypothesis test. It gives us the output from 2 different hypotheses. One is that the power transform is the parameter is equal to 0. The other is the power transform parameter equals 1. All right, 1 means that there is no transform. So a power transform of 1 is, or of parameter 1 is no transform. And that's what's being tested here. All right, this shows that I can be very confident that I want to transform this according to this hypothesis test. Okay, well, this is indicating that it needs to be something in the ballpark of 0. And I get a relatively big p-value on the hypothesis test that the power transform is in fact 0, the log transform. So I'm going to go ahead and I'm going to use the log transform for sub-revenue. All right, now let's do the next one. Let's look at the news revenue. So I'm going through the same process I did with the other two variables. I'm going to use the power transform. I'm going to apply it to the formula news revenue depends on no other variables because it's an independent variable. Now I get my output. All right, so what I notice right off the bat is 0 is not in here. All right, it's not 0, which means I know I'm not looking for the log transform. Well, 1 isn't in there either. 0 is not in there, and 1 is not in that confidence interval. So I want to transform it, but I don't want to transform it using the log transform. So this is a little bit more interesting in the situation. My estimated power transform is 0.0748. Well, what would be a reasonable number in this range? To me, 0.1 is a good choice, so the 10th root. Now, people are not going to be very comfortable with the 10th root, but of the values inside this range, it's a reasonable choice. Now, if it ends up that my audience, my decision makers, are not comfortable with the 10th root at all, I just won't transform the variable at all. Just don't do it. Just stop. If I can't get something in this range that my audience will accept, I just won't transform the variable, and I'll consider keeping the variable or throwing it out based on the situation. And here we can go ahead and we can see, all right, so this is showing me, this hypothesis test indicates that I do not want to use the log transform. And this hypothesis test shows me that I do want to transform it in some way, shape, or form. All right, so here's what I'm going to do. I'm going to transform just the predictor variables right now. So I'm going to transform just the predictors. You notice that ad revenue stays the same, but ad pages, sub revenue get hit with a log transform, and I'm taking the 10th root of news revenue. Now, notice, just like when I did quadratic regression, I've got this I function around the transformed version. That's important. And now what I want to do, I want to look and see, well, how does this turn out? How does this look? Well, I transformed the variable along this axis, and along this axis. So now this is, log, and this is 10th root. And you can see that the predictor variables are now more spread out. But wait, there's more. When I look here, I can see that the log of ad pages and log of sub revenue, that looks like a cloud. That looks like these are independent of each other. So that makes me feel better that having these two in my model probably are not going to contribute to overfitting if I don't see a pattern inside here. Same with the log of ad pages and the 10th root of news revenue. Now, there is a little bit of something going on between sub revenue and news revenue, but when you get real data, you're never going to get a perfect situation. I'm okay with this, considering that, that's how I would proceed in real life. All right, so I have the option of doing exactly what I did by transforming the target variable without considering any other variables. And I can do that here. I don't recommend this in multiple linear regression. It's not such a big deal to doing it sequentially. In simple linear regression, I find that it's not that big of a deal. But here in multiple, because multiple variables have the ability to fit better, this is not the way to go. So you'll notice that as I scroll down, I don't even build a model because I know it's going to be crap. So I'm not going to bother. I'm not going to worry about it. All right, so now what I'm going to do, I'm going to transform the target variable considering the untransformed predictor variables. And I could build a model this way, depending, so I also have to consider like how much of an appetite does my audience have for transformations. For this example, I ended up going with a 4th root, but a 5th root would have been perfectly reasonable also. 3rd root, probably not, because it's outside my confidence interval. So on this pairs plot, I've changed the y, but not the x's. So you can see that vertically, the dots have gotten stretched out. And so it's going to be easier for me to determine, do I have like a linear relationship going on? But I still have everything kind of clumped up on this left-hand side. Now, here's the way I think you should go. I'm going to take the transformed predictor variables, and I'm going to use that to show me how to transform my target variable. All right, so I've got the log of 2 predictors, and then the 10th root, and then I'm putting add revenue over here as depending on these bad boys over here. And so then I get an estimated power of about 0.1. And you'll notice that 0 and 1 are not in the confidence interval here. So I see that hypothesis test tells me that the transform is not equal to 0. It means I don't use log transform. This hypothesis test shows me that the transformation is not 1. Therefore, this suggests that I do need to transform the variable. And so now I go ahead, I build my model. You'll notice I put an I and then a 10th root of the target variable depends on the transform predictors that I established previously. Now let's take a look at the pairs plot. Let's see how this looks. All right, so now you'll see that it's not like a great tight fit. That looks a lot more like a line, right? That looks a lot more like a line. Here, not so much, but from what we've seen so far, news revenue has been like the least important variable. So I'm okay with this how it is. And then I look down at these guys. We've already looked at these plots because these are the transformed versions of the predictor variables. But I just kind of get into the habit of always looking at my scatter plot. So now let's compare our models. Let's take a look. So I've got 4 different models. Vanilla, no transformation. Transform the predictors only. Transform the y variable only based off of untransformed. And then transform x, then transform y. Let's see what we get. And what I want to do, whichever one's the best, that's the one I'm going to run with. So let's take a look. So if I do the vanilla regression, so everything is statistically significant, I can see a 0.72 R squared. F statistic is looking good. All right, let's look at just the transformed X values. Well, I see that my R squared went in the wrong direction. Statistically significant, F test is looking good, but I got to step backwards. That's unfortunate. Now let's look at just transforming Y. News revenue is no longer statistically significant for a non-zero slope. Here, once again, my R squared is going in the wrong direction. F test is looking good though. Now let's look at the sequential transformed. So here, I transformed my X. I figured out what those are. Then I transformed my Y based off of the transformed version of the X's. So remember, I found these transforms first before I went and I found this transform over here. So that's why this is a sequential transformation. All right, well, I can see that everything's statistically significant. News revenue is not as strong as it could be, but it's still looking pretty good. I can see that F-test is statistically significant. And now here, I've got about 0.12 improvement on my R squared. Yeah, honestly, if you get an improvement of 0.12, that's probably as strong as you can get. Anything bigger than 0.1 is going to be like kind of hopeful. If you have like an R squared of 0.6 and you need to get like a 0.85 or something like that, it's probably not in the cards for you. So an improvement of 0.1 is really the most that we can ever realistically achieve for. There are, of course, there are situations that contradict me, such as when there's a nonlinear relationship, but off of just what I've been doing, that's going to be a pretty big increase. But remember, off of what I said, you can definitely come up with contradictions of what I just said about that 0.1. But when I'm talking about like real data that you actually work with, that's about as good as it's going to get. All right, so let's go ahead and accept the transform X, then transform Y model. And then let's go ahead and look at the diagnostic plots. All right, for some reason on my machine, I do not know why, my machine's throwing an error when I do the QQ norm plot on the residuals. So I have that separate. So you'll notice I go 1, skip 2, 3, 4, 5, 6 on this. Let's go ahead and take a look. So here we've got residuals versus fitted. All right, so I'm looking for a pattern. If I see a pattern, that's bad. Now the color goes along with the fitted values. If I had a good model, my fitted values should correspond pretty well to my observed target values, and color corresponds to observed target values. You'll notice that there's a lot of purple. The reason for that is because this is very skewed data. So the original target variable was skewed, so I end up having a lot more dark than I do light values, but that's okay. All right, now let's look at square root of standardized residuals. Look at Cook's distance. Residuals versus leverage. See a good flat line. That's making me feel good. And let's look at Cook's distance by leverage. And remember, we always want to judge things in relation to these contour lines. So I'm more concerned about stuff over here. So Soap Opera Digest kind of popping out to me. All right, now here I'm going to do the QQ norm plot. And this should be a straight line. So if I actually do this, it's going to look like that. So it's a little bit off from the normal distribution. So I might want to be kind of cautious with my hypothesis test for the slope and for the ANOVA test. But honestly, if you have the best model you can get, that's more important than hypothesis testing. So even though I conclude that this is not going to be a normal distribution, I'm feeling okay with this. Let's look at our residual plots. Here what I'm doing, I'm taking the residuals and the fitted values and I attach them onto my data frame. That way I can refer to them repeatedly quite easily. All right, so here let's look at our residuals by log of ad pages, and I don't want to see a pattern. So really I would want to see more of a scattering of, sunglasses prevent me from seeing what I want. I would like to see more of a scattering of the non-purple, but if I see a pattern in the dots, I need to pump the brakes. All right, a lot of dispersion. All right, so I'm feeling okay with my residual plots. Now, let's go ahead and let's look at our fitted values by our observed values. If I have a perfect model, this will look like a straight line. So here, that looks like a line. And so down here is the transformed version of the target variable. Here, this is the fitted values for the sequential transform model. And it looks like a line. It's not a perfect line, but you know, whatever. Now let's do the add variable plot. So remember, add variable plots look to see, hey, should I add this variable when I have all the others in consideration? Well, it's very similar to our ANOVA output. Now, ANOVA always goes in the order of the variables that you go with. So here, this is a hypothesis test asking, should I add log add pages to the intercept model? Yes, I should. This line asks, should I add log sub revenue to the simple linear regression model with log add pages? Yes, I should. Should I add the 10th root of news revenue to the model with log add pages and log sub revenue? Yes, I should, according to this hypothesis test. So this kind of gives me like an idea of what's going on. Now, this is very sequential. All right, so now let's take a look at, in this plot, I'll have the other two predictor variables transformed in my model. If I have those two predictor variables, does log add pages improve the model? The stronger the slope here, the stronger the regression visually, the more I should include it. All right, let's go down here. Asking the same question, should I add log sub revenue when I have the other two variables? Yes, I should. And last but not least, should I add transform news revenue when I have the two log predictors? And here the slope isn't nearly as strong. So this is consistent with this being the least valuable one in my pot of predictors. All right, well, that's all I got for you. Take care and goodbye.